What's up, everybody? Welcome to Earth Science. So let's talk about the two types of earthquake waves in a little bit better detail. Again, the concept we're going with here is just like your thunder and lightning thing, that if you count how much time passes in between those two, you can figure out how far away the event is. All right. So what are these waves? We've got P waves, which we're going to call, we're going to smaller font, we're going to call primary. And S waves, secondary. They have different methods of propagation. That's a fancy word for just moving forward. Don't worry about that. No big deal. All right, so let's check them out. P waves are, yes, they're primary waves. They're also compressional waves, which means if you've ever seen a shock wave, that kind of thing, it's like a squishing and then a rebounding of the land. Sometimes I do this with a slinky. I don't know how I can do that on video though. Let me grab it. Maybe I can pull it off. So we'll see if this works on this silly little camera here. Usually we do this down the hallway. But if we say stable ground is like the slinky, if it stops shaking. A compressional wave or a P wave is like a smushing and an unsmushing. It doesn't look that great on camera. If you do it across the whole floor, it's a little bit more impressive. But hopefully with the diagram, you get the general gist. I'll say it's not going to be super critical either. The big thing is they're really going to boil down to using that page of the reference tables where you see them diverge. So yeah, these travel faster, which is why they get places first, right? Do not cause as much damage. Oh, there we go. There's that classic spelling. S waves are shear waves. Maybe more like the wave motion you typically think of, like up and down like this, which you can probably picture. And again, if I could stretch this thing out over the whole classroom, you can like do a wave and see it travel down. It's just kind of bouncing on this small scale. Unfortunately, these travel slower and are more damaging. And then really and if this is getting into the nitty gritty a little bit more than we need to in regions or science, but when these interact with the surface, they create surface waves. Really what does the damage. But again, the seismometers and the thing that we're doing, the purpose is to just get the difference between S wave and P wave. Magnitude, there's different scales for it. The old one is called the Richter scale, and that's probably like it's still kind of in common verbiage. You'll hear Richter scale here and there. We don't really call it that anymore in the world of real professional geology. It's the moment. Is this the one? The moment magnitude scale. It's mathematically based on the size of the waves. It's like a literal measurement of the size of the waves. It's not a scale where you go from 1 to 2 and then it's the same increment from 2 to 3 and then it's the same increment from 3 to 4. They go up significantly more like stronger than that. So going up from a 2 to a 3 and then going from a 3 to a 4 is like 10 times worse than that. And then the next one up is 10 times worse than that. So it's like a logarithmic scale that really gets up there by the time you get to these high levels. Versus this guy, which we call, and I don't think you'd have to pull these out, these names, modified Mercalli. And what these are, this is more, Reed, what do you see here? This one's actually scanned out of our regions too. These are more based on observations in a local area. Nothing mathematical to say that the wave was this big. More, how did it impact your local area? Okay. And they happen. And this is what we're going to be getting into when we really dig into the mud on this and get into this measurement thing, is we want to figure out where the energy from the earthquake actually happened. Elastic rebound theory, if you've ever broken a rubber band and had it snap and hurt your fingers, you get elastic rebound theory. Elastic rebound theory is that you can put some strain onto rock, onto the earth. It can deform a little bit and kind of retain that pressure. But if that pressure were to magically disappear, it would rebound back to its original shape. But when the pressure is significant enough that it causes a rupture or a crack, then that's like snapping your finger with a rubber band. It does that. Only if you're talking about continent-sized chunks of rock, that's more than just snapping, your rubber band on your finger. It's a serious amount of energy that gets released. Elastic rebound theory. All right, so the energy generally comes from within the Earth. It doesn't happen right at the surface. So it begins at what we call the focus. On a map, though, or what you'd hear in the news, if we were to say, look at this earthquake, they are going to talk about the epicenter. Directly above focus, which doesn't necessarily have to be right on the fault. If you have a fault line that's tilted, then your epicenter is not going to fall on that. Okay. Now, I'm not going to tell you anything out of this little video we just did is like critically important. It's just to give us a little bit of context on what we're going to get into and what it means by S and P. So we've got the P waves that travel faster, the S waves that travel slower, and we're going to try to figure out the time gap in between them, and I'll let that show us how far away this earthquake epicenter would be. It's a bit tricky, but you guys can do it. You're going to do a good job. All right. It will take some focus. This is one of the harder things that we're going to have to work on. I'll do this every video so this doesn't get too long. Keep it up, everybody. You're doing great. We'll see you in a minute.